Welcome to the Layman's Podcast. We're back in 2019, getting back on the horse. You might notice that we're in different surroundings, which is good. We're recording remotely today, and I think that's great for on our side of things for sort of a controlled test to see if we can go and do remote recording, and I can swap this Steinberg mixer out for a Zoom H6 and start doing some trips over east and talking to people. Like some musicians that maybe had almost come onto the podcast but couldn't make it. Anyway, I've got a quick promo to do for Ben McAllister, actually, who was on the podcast not too long ago. He's researching dark matter at UWA as part of the organ experiment. So that was quite an intensive physics sort of episode. If you've seen it, it was a great watch. If you haven't seen it, I implore you to go and watch that one. He is actually the curator of 2 Fringe shows this year in the Perth 2019 Fringe show, which runs from January about now until mid-January, until mid-February. So 2 shows that he's got this year is it's an improvised comedy from Dungeons and Dragons, which is like a self-contained extension of his podcast. It's a live format. His podcast is called How to Win, Loot and Influence Dragons. It's focused on fun storytelling, with each show completely different. So definitely get down and watch them. The shows are Wednesday the 23rd, Thursday the 24th, Friday the 25th. Each show starts at 9:45 p.m. at Lazy Susan's Comedy Den. So that's very exciting. The second of his shows at the Fringe Festival this year is the Uncertainty Principle, which is a science communication show. It looks at the intersections between science and society, stories from history, science, culture relating to science. Each show is different. They have special guests highlighting broad areas of research, which is very exciting. The shows are a conversational format. They're fun. They're not dry and dull. And I wouldn't imagine that they would be. Ben's very articulate and quite theatrical, actually, with the way that he speaks. So I think he's going to bring that to life, and very, very knowledgeable, particularly in the area of dark matter research, which I'm sure is going to come up a few times. Those shows you can catch on Friday the 8th of February, Sunday the 10th of February, Thursday the 14th of February, Saturday the 16th, again, February. All shows start at 6 p.m. and that is on the Veranda Bar at Rigby's Bar, which I believe is just off St. George's Terrace. So check out the podcast if you don't know who Ben McAllister is. That was a really good chat. And then go online and check out the Fringe shows. I'll drop the links in the description so you can check that out. And yeah, try and get down and watch that because I think that'll be definitely really good. So yeah, so today I'm joined by Professor Phil Bland, who is a John Curtin Distinguished Professor at the School of Earth and Planetary Sciences at Curtin University. How are you doing?
Good. Hello, sir.
I discovered you probably about 5 months ago, and it was some sort of news reel of you finding a meteorite. So it was probably what's become one of the most popular stories, I guess, of what you've been up to in mainstream media, which is going out to Lake Eyre and actually finding a 1.6 kilo, I think it was like an iron meteorite. Is that correct?
It turned out to be a stony one.
Okay.
It was. I thought it might be an iron one initially as I was trying to yank it out of the mud, but that was only because it was so sticky and my hand was knackered.
Yeah. I think you said in one article I read that you were like shredding your skin trying to get to it. You were so excited.
It turned out I actually did knacker my tendons in my hand.
Oh, jeez.
I was yanking on it so hard.
Yeah.
So I was quite excited.
Yeah. So that was a culmination of the Desert Fireball Network's efforts in locating meteorites, which I think that sort of the underlying analogy or metaphor rather for the Desert Fireball Network, which you've said yourself, is when you find meteorites, it's like having a bucket of rocks and you don't really know where they come from. It's not really any good to you, but if you know where they come from, then you can start to put together a geological picture. So I think the sort of premise of the Desert Fireball Network, on top of actually like locating meteorites or meteoroids that then become meteorites and strike the Earth, is not just locating them, but also being able to trace their origins back in the solar system and start answering some questions. So
precisely.
Could you sort of run through the Fireball Network, how it started? And
so it's actually, I was thinking the other day, it's I think I've been doing this project or trying to get it going for about 20 years now, which is sort of nuts. So the very first grant that I ever got to just start thinking about it was with 98, which is crazy. And basically the idea is that if you meteorites come through the atmosphere all the time. If you'll see little shooting stars, a fireball is what is when it's something really bright, and they usually last long enough to maybe 4 or 5 seconds, 3, 4, 5 seconds. You can point to it and say, wow, what's that? And your friend can look at it. And so that a lot of people will have seen them. You don't see them that often. If you're kind of used to going out and looking up, you might see one every few days. But basically all of those are bigger chunks of rock, and a lot of them burn up in the atmosphere. But if you land, if we can observe them from a whole bunch of different locations, we can kind of triangulate that fireball's orientation in the atmosphere. And we can use that to plot it back to work out where it came from in the solar system and get its orbit really precisely. And so that's what we do with the network, and then plot it forward and try and work out where it lands.
So with the brightness aspect where it burns up in the atmosphere, I'm thinking of a sort of an analogy for that, where it's like that. So that is due to sort of rapid deceleration as it interacts with the atmosphere.
Basically, it's so they come in average velocity at the top of the atmosphere is around about 20 kilometers a second. The surface kind of melts and ablates, and that all vaporizes, and you get this kind of ionized trail of vaporized rock and gas behind this thing, and that's what we see as a fireball. So close up, it'd be kind of an amazing thing to see. Happily, we're not that close to them all the time, but that's why we see it. It's that deceleration.
I'm thinking of it in terms of like when a car is traveling along at say 100 kilometers an hour, maybe we'll go within the safer realms of maybe 60 or 70 kilometers an hour, and you, for whatever reason, have to hit the brakes, and so you're rapidly decelerating, and then you get like a little trail of skid marks before you're sort of slow enough that effect stops, and then
kind of thing.
It's a bit like that.
Anyone who's seen a movie, of like a re-entry capsule or something like that, in Gravity or one of the Apollo movies or anything, that's basically what's happening. And that's basically what's happening.
It's funny you bring up Gravity, because I had like a really great. I'm still going to use it, even though I'm sort of throwing it out there now. But I've had a great segue into the CubeSat stuff and the satellite tracking for later that I'm going to use. So I'll keep that in the bag for later. Anyone watching can sort of hang out for that one. So I think in 1953 there was one of the first fireball observatories established.
That's right.
And
the idea, that idea of kind of triangulating from multiple locations is an old idea. It's been going on since that time. And that network is actually still going. And so a bunch of people have tried it at different times. I'm a geologist, so I started out as a geologist, and I've done, a lot of field work in the bush. It always surprised me that everyone had put these networks in places where it was really, really hard to find a little black rock on the ground, Central Europe, and so it was basically our thing to let's put it in a place where we know we can find the rocks. Which is why it's the Desert Fireball Network.
So you sort of got almost a clean slate.
Exactly. That was the idea.
Vegetation is not really your friend in this instance.
It's not. No. So the less vegetation, the better.
And so I think the one that was established in 1953, if I'm not mistaken, they found maybe 6 meteorites over like a 50-year, 60-year period.
So it's been going, I think, so that's still going. So what is that now? It's like 72 years, and I think they found 6, over that time.
And we'll talk about that in terms of the success of the Desert Fireball Network. But again, so setting it up in the desert was a massive sort of component of why it has been successful. You guys initially set up a 4-camera array on the Nullarbor. That was the initial sort of trial.
Yes.
And then I assume that you were probably trying to sort of present like a proof of concept to sort of try and get a bit more funding to then go
Precisely.
further than that. So
yeah, basically that's exactly it. And it took from 98 to like 2004 to something like that to get the cash for that trial network, and then 3-4 years to prove that, and then trying to get more cash for the full network. So it's been quite a arc.
Yeah. So in that sort of 3-4 years after you'd set up the network with the 4 arrays, how successful were you? How many meteorites did you locate?
So we got 2 meteorites with that little network, which at the time I think there was only like 12 that had ever been recovered with orbits. So with a really small network in covering just a small area, and really only ever 2 or 3 of those cameras would be working at any one time, because they were actually film cameras with these giant magazines of film, and you're trying to keep an automatic film camera going in the middle of the nullarbor. It was a nightmare. And so just keeping them going was really hard. So to get 2 rocks in that period with all of that, all those other constraints, was a really great result. And with that, we were able to get funding for the rest.
And then obviously in that time, from then until now, the technology is rapidly advanced. So now you're using just a sort of a basic DSLR, and you've got a laptop built into the sort of system, and you can remotely download the information and things like that.
Yeah, pretty much. So it's a DSLR, which is, and then around that we've got, it's actually a kind of, you can get a sort of stripped down, they're called an embedded computer. Actually, are they still? I can't remember. I've got like really smart technical guys who build these things, and but it can do a lot of processing online, and basically talk to the camera, and then process its own images and store all those images. So we've got a record now really of the sky over a third of Australia, that goes back whatever it is now, 3 years or something like that, since we started taking pictures.
So today you now have, is it something like 52 cameras? And that's sort of, I noticed on the map, you've got some down in the southwest sort of region, and then it sort of spreads across more towards South Australia along the Nullarbor.
That's right. Yeah.
That's impressive, and that's covering 3 million square kilometre area.
Yes, it is, and it means that we get a lot more. We see a lot more fireballs. We've got a lot more potential to go out and look for stuff. We get. But it's also what we realized we could do is actually get, it's not just about finding the rocks. If because we were seeing so many that we thought, okay, we've really got to try and work out orbits for all of these things, not just the ones that we think might have a meteorite on the end of them. And no one had done that before, so we had to kind of do this massive automated, you call it a data pipeline, which is kind of to crunch all of the data. And so now we've got a data set, basically everything that's been hitting the Earth in that size range, in those rocks, where it all comes from. It's about 1,000 orbits now, which is bigger than the entire extant literature, which I'm really chuffed about, and it looks so cool. So these colleagues have kind of done a visualization of it, where in kind of you got a 3D view of the solar system, and it's like you've got a camera sweeping through it as all of these objects are circling the sun, and then just coming in and hitting the Earth. It looks incredible.
Wow.
Yeah, it's very.
Can you view that
gorgeous.
online? Is that
I don't know if we've loaded it up. I don't think we have, but we should do. Yeah, blooming heck.
That would be pretty cool.
That would be really good. I should do that. Yeah.
And I think you guys are getting a bit of help on the big data side of things from Pawsey across the road.
Absolutely.
They're local.
So we've been working really closely with Pawsey for several years now. And all of our data is stored on the Pawsey data store, but we also use the supercomputer to crunch all our data and to do orbital modeling. So we use that resource a lot. They're
brilliant.
awesome.
So that would, I think, if I'm not mistaken, that's the largest supercomputer in the Southern Hemisphere.
It is, that's correct.
Which is just right here in the middle of Bentley.
It's fantastic. Yeah, no, it's awesome resource for the state. Yeah.
It's wonderful. So what I wanted to ask as well, these are just going to be, there'll probably be a litany of basic questions from me just to sate my curiosity.
Yep.
What's the difference from a geological perspective of finding a meteorite versus, a meteorite from an asteroid versus from a comet? It seems as though finding a comet is like sort of you've hit gold,
Yes.
you know, in some sense.
Basically, a comet, as far as we know, and we get, you know, tiny little bits of dust from comets that hit the atmosphere all the time. Some of those we get in fairly good condition, but they might only be 20 microns across. They're tiny. But comets still have water on them, and so we know they've not been cooked up too much. They've not seen too much geological processing. The exciting thing there is that so meteorites, those sorts of meteorites, a lot of meteorites date from really the earliest period of solar system history. So the sort of dust in a comet and some of the material in a meteorite, formed within just 10, 20,000 years of the sun starting to shine. Yeah. Some of it predates our solar system. And comets, because they've had the least amount of kind of processing on the object, they've got more of that pristine material, so they you can get further back in time in terms of trying to understand the solar system history. So to give you a feel, the Stardust mission to try and recover little bits of comet dust, that cost $200 million, and I think it was 1 milligram of dust that we got back from that. So if we could recover a cometary meteorite and actually have something that's sort of, tens or hundreds of grams, that would be really cool. Yeah, that would be awesome. That would be very nice.
So a unique sort of characteristic of our solar system that's sort of, I guess, where these meteorites are hitting the Earth, a lot of them are coming from the asteroid belt, which is sort of located between Mars and Jupiter. And then could you maybe explain a little bit about Jupiter's role and why that exists and the importance of that?
Absolutely. So the asteroid belt is there because and some people think it's always been in roughly that position. Some people think basically it was kind of put there as Jupiter migrated and changed its orbit in the early solar system. So some people think it's kind of always been there, but it never accreted into a planet, essentially because Jupiter kept disrupting that. Another idea, is that kind of as Jupiter moved around in the early solar system, the planets that we know today probably haven't always been in their positions from the sun. And that's also a possibility that it kind of was constructed within a few million years from all the debris that was around from within a few million years of the sun starting to shine. But basically, our solar system has this debris ring that's made up of, like compositions of, we get, as meteorites, we probably get at least 150, maybe 200 different objects from the asteroid belt delivered to us for free. We don't have to go there. We're getting all this material, and so really, I guess, with the Fireball network, it's about kind of getting the most out of this freebie, free material that we get. To if we can work out where it comes from, then it really helps us understand solar system history. Astronomers can tell when they look at other planetary systems whether those systems also have debris disks. So we're certainly not the only one that's got that. There are other planetary systems that have that. But it's I guess pros and cons that we do. The pro is that we get this material as meteorites. The con is that we get large impacts on Earth that can be a problem for life. That's
an interesting point. Throughout time, like are there any significant impacts off the top of your head that we know have occurred? I mean, obviously with the extinction of the dinosaurs, but I mean, I was listening to a lecture, and this might be an absolute whopping exaggeration, but I've heard that there's been impacts that have been significant enough that they crashed in, gone, I think, kilometers and kilometers deep within seconds of striking the Earth, and then created tidal waves that are hundreds of meters tall and traveling at 4 or 5 times the speed of sound. You've got to sort of stop yourself and kind of wonder if these numbers are accurate.
What would that look like?
But there's such a disconnect between the small scale events that typically happen on Earth, although volcanic eruptions, earthquakes are magnificent. But then someone has said it before that we are just a little planet in a shooting gallery, you know, like these are like unbelievably powerful things.
Yes.
Like it feels like life is so impermanent and just and
I think fleeting. I mean that is true, and you know we do. The Earth does get hit by. It is true, you know, little planet in a shooting gallery. I guess on the bright side, it's a shooting gallery that doesn't get that many visitors.
Yeah,
do you know what I mean?
Thankfully,
so, which is good. And but in terms of when a big one hits, then it does generate incredible effects, and it's roughly kind of 20 to 1 in terms of, so if it's a 1 kilometer diameter asteroid, you might get a 20 kilometer diameter crater. And something like that hits and you'll get a gigantic tidal wave moving very, very fast and would make a mess of Pacific Rim kind of thing. That would be a bad thing.
This is probably more for the doomsday people, but and I don't want to linger here.
No, you're fine. Yep.
But what is the reality of how well are we actually able to detect these kind of life threatening sized bodies in space that could potentially strike the Earth? Because and my facts are way off here, but this is sort of in the realm of hearsay. But I have heard that there have been big bodies that have moved within 1 lunar distance of us, and we haven't even detected it until 2 or 3 days after it has passed us. I think this was in the 70s or something like that, potentially, or 80s. Whether that's true or not, but do we have a good idea of when things like this are moving towards us, and do we have time to even be aware?
So that's a good question. So there's a couple of different aspects to that. There's the kind of, are we threatened by anything big enough to that 20 kilometer diameter crater, 1 kilometer diameter asteroid is most people's kind of cutoff for a sort of a global problem, because it would throw enough dust in the atmosphere to kind of wipe out a season's harvest. And that's the thing that would be an issue for kind of our very connected agricultural food network. There was a big program that NASA started called Space Guard, which was built to try and work out, to look at all the asteroids. Can we detect everything bigger than a kilometer? And we can say that pretty much there's virtually no chance that anything of that size is going to hit us in the next 100 years. So they mapped out all of those, and so there's not going to be something now that beyond 100 years, orbits start to get a little bit more uncertain. So the reason it's kind of 100 years is you've got to run that orbit forward on kind of a clockwork model of the solar system, and uncertainties get bigger and bigger. And so, but if you keep on observing, then you can keep on setting that clock back. So from that point of view, we're pretty safe. For smaller stuff, it's flying through the Earth-Moon system all the time. And on the order of 100, 200, 300 meter objects every year coming in the Earth-Moon system. But the volume of space there that's defined by the Earth-Moon system is massively more than the volume of space that the Earth takes up, that cross section. And so we're still pretty good. The things that are an issue are kind of Tunguska sort of events, or Chelyabinsk event where something blows up in the atmosphere and it has local effects, local on the scale of maybe hundreds of square kilometers or a couple of thousand square kilometers. So it's like a nuclear airburst.
Yeah.
And if that is, over a city, it's very unlikely that that'll happen because the area of cities is actually quite small. But if that does happen, then that would be that's a problem. Yeah.
Yeah. So when we're doing that kind of modeling, so there is a value within the calculations that is like an uncertainty that extrapolates over time. And
exactly.
Okay.
So the way people interested in that sort of work do it is that if there are ones you can basically tell, okay, there's no chance that this thing's gonna hit us, but maybe 5% have a question mark, and so you analyze those.
Right.
You observe those 5% more, and you get rid of 90% of them.
Yeah.
And then you look at the 10% that are left, and you spend more telescope time to look at those, and you can whittle it down like that. So that's the sort of process that happens. Yeah.
That's interesting. Yeah. I didn't know these things were sort of going on. I mean, I suspected that there was some kind of attention, but that's a cool process.
It's absolutely. And NASA have got a program now trying to find the smaller ones. So get down to like 100 meters, that kind of thing.
Okay. So I wanted to sort of do like a little bit of a thought experiment sort of scenario where we run through like when you like essentially establishing a new camera in the array, and then let's say that is actually the camera that was to detect a meteoroid that then became a meteorite. And Am I right in that? It's a meteoroid until it hits the ground.
That's right. It's a meteoroid in basically until it hits the ground. Okay. So it's a meteor or a fireball is the light that it gives off.
Yeah.
And it's a meteorite when it's on the ground.
Okay, great. Yeah. So just going through establishing a new camera, that one making an observation, and then could you run me through sort of the entire process?
Yeah. So the camera, we spent quite a long time designing those things, prototyping them, working out, okay, what works and what doesn't, getting them so that it takes quite a long time before you get something that's actually going to can survive for, a year or two in the bush, and it's quite hard to predict what's going to fail and what's not. So that took quite a while. Now we know pretty much, we've got that locked down pretty much. So we usually build a bunch at one go. We're currently expanding the project globally. So we're building like 40 in one go, and then sending those out to collaborators. When one of them gets a camera, or when we take one out, we'll drive out to that spot, put together a stand. We've got kind of a prefab sheet steel stand that we can put together pretty quick. Solar power system that's attached to that. Camera gets set up, kind of bolted onto the stand, and then tested to make sure that it's in focus, that all the electrics are going. We'll observe for a night, and then leave it, and it's there clicking away, hopefully quite happily from then on. Then every night the software looks at all the images that are coming in. It takes a new exposure. It takes long exposure, so a 30-second exposure, and then it starts a new one straight after. The software on the PC looks at all those images, and if it sees a fireball, if the algorithm sees a fireball, sends it as an email to say, I've seen a fireball, and then we download that. That all happens automatically. Yeah. And then the rest of the system is all kind of here at Curtin, part of our kind of that automated pipeline to pull together all of that data and convert it into orbits. And that is a lot of people time went into it. It turned out to be as hard to do that as it was to build and deploy the hardware. So just wondering,
the 30-second exposure, how did you come to that decision to have that length of time?
Yeah.
Is that related to how quickly they're traveling when they enter the atmosphere?
Not so much. It's basically that longer than that, and the stars move far enough that you start to get star streaks. They look like little streaks.
Yeah.
Shorter than that, and basically the longer you can get, most cameras kind of fall over. The shutter dies after a few 100,000 actuations.
Yeah.
So if you can kind of stretch that a bit by having long exposures, then that's good. But more than 30 seconds, and you start to get long stars.
Lots and lots of meteorites.
Yes.
Lots of meteoroids, rather. So talking about, where were we just then with the cameras? So I lost my trail of thought there.
Yeah.
So you're using fisheye lenses as well.
Yep.
Which is, some of the images are like really spectacular, and not just of the meteoroids, but also there was some natural like lightning storms and other features that were. I even noticed you put together sort of a slideshow that was like kind of like a moving sort of like stars, and everything was kind of going out. That was awesome.
I love those. And so the fisheye lens basically means that, the whole horizon is kind of wrapped around in a circle on the image.
Yeah.
And so it's a little bit difficult to get your head around at first. But sometimes that's right. So the cameras are designed so that they switch off if it's cloudy. But sometimes, in Oz, you can get a lightning storm, and a big part of the sky is still clear, and so we've got great examples of kind of lightning happening all around, and I love those.
Yeah,
and others, like you say, where we can kind of stitch them together in a movie, and you can kind of see the stars sort of moving through the night across the lens, across the the sensor, and what that looks like, and planes flying over, if it's planes or satellites. It's gorgeous. I love those.
Yeah, it's brilliant. Astrophotography is, as a wider field, is just like incredible.
Yeah.
It's nothing obviously captures that better. Like, because I feel like a lot of people, they're just kind of completely unaware of the night sky. They just kind of go, but often like. Yeah, most nights actually I'll sort of poke my head out and just have a look and wonder. Like, in
Australia, we're so lucky because a lot of places, even in Perth, on a good night, if you're in a park or you're away from direct lights, you can see the Milky Way sometimes, which is just crazy. And you go out of town, and you get really clear skies. And the southern sky, we got the Magellanic Clouds, we got little satellite galaxies. It's gorgeous. So I love it. Yeah, it's beautiful.
I want to get out to the observatory up in the hills and sort of have a poke around there and see, because they're always putting on different events and things.
They do. It's lovely, and we had a camera there for quite a long time. They were helping us out with that. Yeah, they're really nice people.
Yeah. So you guys you were saying the astrophysics and the orbit sort of modeling, that's quite a significant chunk of manpower and time. So that sort of summarizes the section of looking at sort of what the meteorite was doing before it hit the atmosphere, and then you'll do climate modeling as well, which is sort of once the light goes out, then you've sort of got to go, well, what's the wind doing, and various other factors.
So basically, So when we see the thing, we'll do that first triangulation. So we'll work out, where it was. We'll put together all the data from all the cameras, work out exactly where it was in 3 dimensions as close as we can, and then we'll try and model the deceleration of that object, and so and whether it fragmented at any of those points, and with the deceleration we can try and get an idea of the mass, and then we can see, we can try and look at, based on its brightness and our estimate of the mass, can we get a feel for density. And so there's a really complicated model there, and shape, and so there's a few of these things are real, we are big unknowns, but there'll be somewhere in the middle and all of that modeling that will be our best estimate of mass, shape, density.
Yeah.
And then we look at a kind of a wind model. What was the weather doing in that volume of sky when this thing came in, and that's a 3D wind model that we use for that, which is quite sophisticated. And then we try and project all of that down onto the Earth's surface. So the thing will, the light goes out, when it decelerates down below about 4 kilometers a second. And then you basically have to just use all that modeling to try and work out where it went in the couple of minutes, maybe, while it was falling from 30 kilometers up.
Right.
And that's quite, and then you get into the kind of, okay, where on the ground would that thing have hit? What is the kind of range of possibilities, based on mass and all of shape and all of that? And then you get into that sort of 3-4 square kilometer error and uncertainty. Yeah.
So after you telling me this now, and then just like seeing you sort of, digging through the ground and actually lifting up that meteorite, that to me is like the epitome of when someone in maths class is like, why do we need to know this? And it's like, well,
it's
we
true.
can actually pinpoint a 1.6 kilo object that's fallen from outer space using advanced modeling techniques.
Right, exactly.
Wonderful.
So that one came from I think about 3 AU out in their asteroid belt, and we can say exactly where it came from, and in the atmosphere, we can pinpoint it when the thing is a fireball to within maybe 50 to 100 meters, which just blows me away that it's possible to do that. I think it's just crazy. I love it. So I've got some amazing people who do they've done an incredible job of this.
That's unbelievable. What goes through your mind when you sort of pick one of those up out in, like, for instance, in Lake Eyre, and you actually get that rock out and like?
Well, I mean, that was the reason, that was an amazing experience, because it was kind of the first one we'd recovered since we'd built this complete new system.
Yeah.
With this, all new hardware, all our own kind of data reduction, all automated. And to be honest, you don't really know if the thing is going to work.
Yeah.
Right? And as a scientist, you kind of, you want to sort of, you're writing grants to do this work, to get these projects funded and everything. But you don't know if it's going to work. And this was a really big unknown, with all that hardware, with this lens, with this sensor, with the way we record images, with the way we get the timing information, and then with all that data reduction, are we doing it right, or have we screwed something up? And the only time is when you pick the rock up, and that was very nice, actually. Not just from a science point of view in terms of what we can do with it, but in terms of like validating all of that effort.
Now, once you've actually got the meteorite, and what's the sort of analysis that then goes into looking at the composition, and what can you learn from that?
A lot. And so what we do is there's a whole bunch of kind of baseline analyses that we do that give us information about what sort of asteroid they came from, what its history was in the early solar system, it compositional history, how it, the geological history that it had in the early solar system, possibly like whereabouts it might have formed. So we analyze a whole bunch of different isotope systems, oxygen isotopes that we think might have, there might be a kind of stratigraphy, or they might have changed in different parts of the solar system. Different solar system objects have different oxygen isotopes, and chemistry, its density, its porosity, and then with the orbit we can try and put that together in terms of okay, we think it came from roughly here. Does that make sense in terms of the things we're seeing in the composition? So that first kind of analyzing the rock process, we've got it's like 12 or 15 collaborator institutions internationally that are part of that. So when we get a new one in, that's what we send out, little tiny bits of it, and they do all that work.
Yeah. And outside of the Desert Fireball network, we've also recovered rocks from the Moon and Mars, which is, I think that again sort of highlights the point that you were making before, where you can spend hundreds of millions of dollars trying to get to a place, but there's also you can't underestimate the fact that we have things that are landing here all the time that can tell us an awful lot.
That's right.
Like on a budget as well. So.
And it's basically, and I think, those, so I'm part of the Acerous mission, which is bringing back a sample from an asteroid. And that's going to be incredible. The material that mission will bring back it's going to be the most pristine and oldest material that we've ever recovered, right? That geologists have ever been able to analyze. It's going to, I think if there's anything that can kind of completely revolutionize what we think about the early solar system, then that'll be it.
Yeah.
Really, I think you can think of our project, the Fireball Network, and the expanded one as kind of a complement to that. It's like we are getting all this free stuff. How can we get the most value from it?
Yeah.
And that's the way I see it.
Yeah. When was the Acerous mission launched?
So that was launched in, 2017?
Okay.
2017.
And
is that right? I think so. God, it's been a long couple of years. I think 2017, yes.
And that's where is that actually traveling to?
So it arrived at the asteroid Bennu in December last year. So just a couple of months ago.
Yeah.
And now it's orbiting that asteroid. It's going to be basically doing a lot of analyses of the asteroid itself, of the composition of it. I think for 18 months before trying to grab the sample and then bring that back. Basically, that sample grab is the most dangerous part of the mission for the spacecraft, and so the mission planners want to basically have a whole bunch of data value in the bag before they take that risk,
potentially destroy the
exactly. So but it'll be incredibly exciting. And so in 18 months it'll do that, and then bring that stuff back, and it'll be it's the material will get it back in 2023, and here at Curtin we should have some of that to analyze. There's a team, and we're part of that, and we should be getting some of that to play with, which would be fantastic. Yeah,
that's unreal. That's
it's going to be so cool.
Yeah. That's actually probably a good segue into the asteroid Ultima Thule.
Right. Yeah.
It was the flyby that happened on the 1st of January this year.
Sounds right. Yeah.
So, how much can you sort of weigh in on that? That's my understanding is that it's been described as a low cratering asteroid, which I think that translates roughly to it's relatively pristine and can tell us a lot about.
I mean, I think it's so basically you've got the asteroid belt in the inner solar system. The inner solar system is everything interior to Jupiter. Outer solar system. You've got another debris disk, which is called the Kuiper belt, and that's Pluto is part of that.
So that's trans-Neptune.
Yes,
I've heard that term being thrown around.
That's right, further out than Neptune, exactly. And so New Horizons, which is that spacecraft, which is an awesome. I mean, I think it's the fastest object that humans have ever built, right?
Yeah.
Which is so cool. And did a flyby of Pluto and gave us the first view of Pluto, which was astonishing. I mean, the amount of, changed, loads of people's view of kind of what was happening out there, because you got completely new surfaces on this object. So it was in some way, geologically active, right? I mean, it's very, very cold out there, right? To have things, and it's, I don't know, nitrogen tectonics or something, it's fascinating.
Yeah.
But what they realized is, after they did the Pluto flyby, is that there were other objects that they could potentially visit, as the probe is not it's not built to orbit. It's going out really fast so that it could get to Pluto in good time, and it's flying out the solar system really fast, but they could nudge its trajectory a little bit to fly past this other object, Ultima Thule, and see that. And it is a weird looking thing. It looks like a kind of a dumbbell of two things that kind of stuck together. And there's not really any craters, I don't think, on its surface, and really I think that's down to I've not read up on this, but my guess is that the density per unit volume of debris out there is so low that you're not going to get hit that often. I think, but I can probably be wrong about that.
That's right. We're often wrong on this podcast, so that's the nature of, from our side of, anyways, trying to engage in conversations like this. It's like we're we're doing our best. Good. But I love this stuff. So I have heard it being described as a snowman as well, and that's really interesting to me, because it's like you're talking about one of the farthest objects that we've ever sent a man-made craft to be described as something so colloquial as a snowman. It's just like, wow.
Which is kind of weird, isn't it? I love that.
To see something out there and be like, snowman.
I love that. But I also love that, one of the, I can't remember which Voyager it was, one of the Voyager spacecraft, has now left the sphere of the sun's influence. We're sending stuff out now into not just exploring the solar system, but interstellar space, which is gorgeous. Great to live at this time.
It's just, it feels good. We're sort of getting further and further, and I'm a big proponent of us becoming a spacefaring species, and it just has to be an option. I don't want to sort of be that guy that says, oh, we need to find another place to live, and on that side of things. But just from a curiosity standpoint, I think that how could you not? We're sort of biologically wired to always want to venture into the unknown.
Right, exactly.
There just seems to be so much out there that needs to be discovered.
Humans, we explored, we went all over the Earth as soon as we could, as soon as we invented the technologies to do it, for the Polynesians, in canoes. They've found, every tiny little island that was going. It seems to be in humans' nature to do that. I think it doesn't make sense to me that we would choose not to, with having the technology to explore, choosing not to. Why would you do that? I heard for donkey's years, sorry, just to continue that thought, it's so expensive, space programs are so expensive. I think it was illustrative in 2008 with the financial crash, just how much governments are willing to spend on
bailouts
on bailouts. I think Royal Bank of Scotland, it was a couple of $100 billion to bail out Royal Bank of Scotland, and NASA's budget now is $20 billion. So basically, Britain could have had a solid 10 years NASA budget or bail out Royal Bank of Scotland, and I know what I would vote for. I think mission to Mars, like human mission to Mars, is $100 billion. So Britain could have gone to Mars twice, or bail out RBS. Take your pick.
And it's I can definitely say, for the two sides of that, you've got the banks and you've got NASA and things like that. it's not like NASA isn't throwing mountains of evidence and scientific reasoning behind their budget proposals.
Right. And it's, when those things happen, like when Curiosity lander, landed on Mars, it was like everyone in the world was just blown away by that. Pictures of all those engineers in JPL jumping up and down and going bonkers. And then all the images that it's taken, all the discoveries that it's made, I think it gives people a sense that there is more that, we as a species are doing, this amazing stuff. It kind of raises everyone's game a little bit. And I love that. Yeah.
I think that the argument that I often hear in terms of like why spend so much money trying to do that when there's problems back on Earth, that one sort of grinds my gears a little bit, because the amount of technology that we develop to do those missions and the applications that they have on Earth is staggering as well. So it's sort of it's two birds with one stone. It's really not just pouring money in one area and then leave everyone to die. It's
I think ESA did a study of how much gets what's the kind of value, like cash return really, in terms of funding for space programs versus how much do we make out of that and for space industries and everything else. And it's about 5 to 1. So a country spends $5 for on space. Okay, that's not a normal amount. Like $100 million on space, they'll make $500 million out of that. So it's kind of not to do that is sort of a bonehead investment. I mean, the reason why, you might say, okay, why do you want to do a mission to Mars? Well, I got into just one example. I got into research. I became a scientist, because I grew up looking at newsreels of Apollo, right? And I think there are probably hundreds of thousands of scientists and engineers who started their careers just because of that. So it, quite apart from all the other things that come out of those, all the other kind of technological innovations. I mean, it basically, I think one of the first implemented computer programs was on the MIT built for the LEM, for the lander for Apollo. And that's kind of a big deal, computer programs that actually manage systems. Little tiny things like that have turned out to be quite useful. So I think you get a lot of value out of that stuff, even though it might not be obviously immediately have an economic spin-off.
That's probably a good segue into the Australian Space Agency and what's going on there. So that was established, I think, last year. Scott Morrison announced this year that Adelaide was going to be the new home of the Australian Space Agency. So
it was the review started into basically what its remit would be. That started last year. It was formally inaugurated. I think it was like beginning of July this year. Okay. Sorry. Last year. We're 2019 now. I'm sorry. You're right. Year before.
Where's all the time going?
Etc. Yes.
Briefly wanted to, as much as we could sort of hit this topic of the Australian Space Agency and opening it up with the question that what do you think the next 10 years would look like for the Australian Space Agency, and where might their focus be? I don't know if that's going to be in the realm of CubeSats and smaller like payloads to space or...
I think, I was initially a little bit concerned the way the conversation was going, because a lot of people were talking about it was just going to be purely industry. And of course, Australia isn't going to do missions. And of course, we're not going to do, and really you look at it in the rest of the world. I'm involved in, I was there during the formation of the British Space Agency, and I work very closely with colleagues in NASA and ESA. There's a reason why all of those organizations do missions. It's because of that 5-to-1 investment payoff,
Yeah.
right? We're a little group here of planetary scientists and space scientists and engineers. We have a whole bunch of I've got a whole bunch of students here who are building a CubeSat, right, from scratch. So a small satellite. Corporations, I mean, that's honor students at a university. If I was going to, the cost in terms of the person time cost of that is so low compared to the person time cost of a corporation trying to do it. You get massive value from having universities engage in all this stuff, from having honors students and PhD students and academics do this sort of work and generate this, this intellectual property and these innovations. It's a real bonehead choice not to include that in the remit of something like that. There's a reason why all those agencies include it, and so it's a big deal for me. In 2017, I'm getting my years right now. We went on a few visits to Canberra and a few visits and conversations with other policymakers to make that point, to basically say, look, missions often pay for themselves. Yeah, it might cost tens of millions or a couple $100 million, but they often pay for themselves in terms of the innovations that they generate. And it was, I think, I don't know if anything I said helped that, but certainly the agency, I think now, although it's still very focused on industry, and it should be generating an Australian space industry, there's an acknowledgement there and a recognition there that it's vitally important to have aspirations to do more, to have that we will collaborate on missions, that kind of blue sky component of space science and research won't be written out of the remit, which is great.
Yeah, it is. It's incredible, and there's a sense for me, because I have spoken to other people at Curtin, notably Jennifer Lane, who's I mentioned when we met earlier this week. She's studying interior architecture. She's doing a PhD looking at designing Mars habitats, and not only the habitats that we would deploy on the planet, but also what the insides of the transit sort of craft would look like. And there's a heavy focus on psychological health and trying to, because I think it's like a 7 or 8 month transit to Mars, and it's like being sort of in an enclosed space with a handful of other astronauts. It's could present as one of the biggest challenges, really.
Absolutely. Being with a very small number of people is the hardest thing. Yeah, absolutely.
So having sort of been around the traps here and then talking to yourself and all the research I do online, there seems to be a real sense that Curtin, there is like a really heavy space interest at Curtin specifically.
Yeah.
And as someone who has a personal interest in that topic, living close by, actually studying at the university as well, that's very exciting. It's extremely exciting.
It's great, and it's great that the university is supportive of that and recognizes that it's an exciting area, that it's a growth area, that we can attract students, with some of these projects, and it's lovely. I'm really glad that this is all happening. It's great to be part of it. It's great to be helping to make that happen.
Yeah, that's wonderful. And who better than to try and get into space than a bunch of starry-eyed students? Excuse the pun, but they have that ambition and drive and the wonder that sort of you have at that age, and it's brilliant. And that's sort of getting me into the topic of like what really set you off on this trajectory for your career. From I think you graduated in '91 from University of Manchester in geology.
That's right. And so I was the first person in my family on either side to go to uni. No one had done that. I only did it because I really didn't want to do what my old man had done, and I just wanted to. He worked at Rolls-Royce for like 20 years, 28 years, and hated it after the first year. And so, but that was kind of the, everyone, you be with coal mining or steel or something like that. And so I want to get out of that. I did geology because I like hiking. I did an internship at Natural History Museum in London on meteorites. When I graduated, I had a really great time in Manchester. Late 80s, early 90s in Manchester. All of those bands, right? It was awesome. And so I had a really good time.
So who are we talking about there? Like the Sex Pistols and that sort of punk scene?
No, not that old. God. And Happy Mondays, Stone Roses, New Order, all of those guys. Yeah, and it was fantastic. And so so I was very broke when I left, and the bank didn't really want me to do a PhD, right?
Yeah.
So I had to get a job. Now it just so happened that there was a job going as meteorite curator at another university, Open University, which is kind of a has a campus, but there's no undergrads on it. It's distance learning, but it's a research campus. So I went there, ended up doing a PhD kind of in my spare time, and getting it pretty quick. And the PhD was meteorites, and so I kind of got into it by chance, really.
Yeah,
and I've loved it since then. Yeah. So
brilliant. That's great. So that was sort of something an interest you developed as you were going along with it. As a child, were you very interested in space? And
I was. Yeah. I was fascinated by it, and that came out of a school project, and I did this one project on, it was like fauna of Britain, and I did all these nice drawings and everything. It got a good mark, and for the next one I picked space flight, and I didn't do any. I was just reading every single book I could find, everything in the school library, everything else I could get my hands on, and I got a good mark, even though I didn't write anything because the teachers saw that I was kind of into it.
Yeah.
But I never dreamed that I would end up doing that I would end up working in that. I just didn't come from a place where anyone did anything like that. So I remember going to a careers day, and I'd just seen Jaws, right?
Yeah.
And I loved Richard Dreyfuss' boat, right, in Jaws. It had all these down-pointing lights all around. It's so cool. And he's a marine biologist. And so at this careers day, I go in, and the woman behind it, and I say to the woman, I really want to be a marine biologist. And she looks at me and sort of shakes her head sadly and says, you need a PhD for that. And what she meant was, no one in Derbyshire has ever done it. It's like you don't aspire to anything like that.
Yeah.
And it
wasn't an option in
not
people's
an option.
minds.
No, people just don't think like that. Well, they didn't then. And so yeah.
Derbyshire, is that like a heavy sort of working class kind of? You just sort of get your head down and work and try and make a sort of cut out a nice living for yourself.
Exactly. So it was always big coal mining when that was still happening, and obviously a lot of jobs got lost in that, and big steel when that was happening. So it's kind of, post-industrial now, but big, working class really.
So you really, in a sense, outgrew that kind of mentality in that place and needed to go abroad and.
Yeah, but only not really because I thought I could it was more kind of I think it's easy to think about these things in terms of some nice story of kind of, vision and growth.
The dream,
It was more stubbornness and anger. Anger at being kind of at having no options.
Okay, so it was more of a a push away from that situation you didn't like, rather
Yes.
than a pull towards something.
Absolutely.
You
I
envisioned.
simply didn't imagine that any of that other stuff was possible. I just knew that I didn't want to be there.
Yeah.
Yeah.
Wow. And then obviously going into geology because you liked hiking. It was so even then the decision making wasn't following that trend of, well, I don't want to be this and then go
Yeah.
for the PhD in that. It was quite a sort of an arbitrary decision to do geology, but
Absolutely. I just knew I loved being outdoors. I'd done a little bit. There'd been a little bit of geology in the geography, that I did as a school student, and yeah, I loved mountains. I loved mountaineering and hiking, and so I wanted to do it because of that. Yeah.
Yeah. My parents are from the UK, and my dad as well is massive on hiking. Do we need how are you doing for time anyway? Just well.
I'm good.
Okay.
I'm good, man.
Yeah, my dad loves his hiking and was in the British Army and just got me into it from a young age. And my co-host, who's unavailable today, as people would probably have noticed, he's big into the hiking. So we love it. Like we'll go out. I think a couple of months ago we did Bluff Knoll, which was cool.
Nice.
It's definitely one to do.
Yeah.
And we've done the Bibman track before, and we wanted to do the Cape to Cape as well.
Yeah, gorgeous. I
couldn't
want to
work
do
the
that as
time
well.
out.
Yeah,
Yeah.
fantastic. I was out in New Zealand over Christmas and doing some hiking there, and it was so great to do that again. I've been so long since I've done that. I used to do a lot in the Alps, and it's been donkey's years. It was so great, and so I want to do much more of that. I loved it.
That's the best. There's something about that sort of being in nature, getting out of the city, and you get like a clarity over your thoughts, and
Absolutely.
it's definitely, and obviously the physical exercise is excellent as well, which has always been a big part of it for me. I'll sort of round back in now to the CubeSats. You mentioned it when I met with you earlier this week that you're working with some students and they're trying to sort of design and manufacture a CubeSat, and they're normally, the dimensions are normally 10 by 10 by 10 centimeters.
That's right. So they really are tiny. So you're trying to pack in, all the electrics that you need for the operations of that thing, all the communications that it needs to talk to the Earth and you talk to it, all of the the power, like solar panels on the outside and the battery on the inside, and then a payload, whatever it is you want the thing to actually do. So whether it's imaging or something else, and in a 10 by 10 by 10 cube, which is quite a challenge. And, but that form factor, that the CubeSat kind of unit, has become really, really popular, and you can have kind of three stuck together and doing different things. It was a thing for me that there are universities and colleagues, research groups in the States that have had student teams building that, and I thought, well, why not? Let's do that here as well. It's certainly within the skills capacity of kind of good undergrads and PhD students. So we put together a team. We were really, really lucky. So me and some of my staff engineers on the Fireball project, and we just got this awesome team of undergrads who've done a great job. Happily, 3 of them have carried on and are going to be doing PhDs in the group on that project. We've got some more undergrads now started this year, and it's really coming together well. And so we should, hopefully have be in a position to launch our first one maybe by the end of the year. So WA's first spacecraft.
That's incredible.
So cool.
Yeah.
So I can't wait for that. I think it'll be awesome. Yeah.
And so these are relatively cheap to manufacture, and
comparatively, they really are. And I think having the capability to do that in-house and building those skills means that, so the idea is that we're not going to stop with that first one. We're going to, it's part of a program that we, hope that within 5 years we'll be able to build something that goes, I can't call it deep space because I think there is a technical definition of deep space, and this isn't it. But to the moon, or to one of those asteroids that you mentioned that flies through the Earth-Moon system, so to do something really quite challenging, but in a kind of a major Australian mission sort of concept, and I think we're on course to do that. Yeah.
Wow. That's incredible.
Which would be awesome. I would love that. Yeah.
I got sort of carried away reading about the different propulsion systems that you can use on them. That's quite cool.
So cool. Yeah.
It's kind of like it's easier to wrap your head around than rocket propulsion.
Yeah.
In a sense, but it's sort of like bleeds into that in the terms of the physics and the understandings and the various types of systems you could have. It's like a watered down condensed version. For someone like me who's rocket science like illiterate, it was cool to read about like sort of the chemical propulsion, and then I believe that some use nitrogen, like compressed nitrogen gas, to just kind of like spray it out to rotate it.
Yeah. So there's lots of different options, and people have explored lots of different options, and it is really exciting, and I find that fascinating as well. I've done that kind of thing as well.
Yeah.
And a lot of those, haven't been tested that much. They're kind of concepts. I think that'll be a thing that we'll get into to test those more. Yeah. To test some of those and see, what we could use to kind of get to the moon or intercept an asteroid, that kind of thing.
Do you guys have any rough ideas about what you might lean towards, or is it you're completely a blank canvas in that
in terms
area?
Of propulsion?
Yeah.
Well, I know the one that I think is awesome, but it's just, I think, way over spec for what we would do, and that is an aerospike engine.
Okay.
So I love these. So it's kind of an inside out rocket engine,
right? And
it's way over spec for a CubeSat. The thing would be just going off at some ridiculous velocity.
Yeah.
But they're gorgeous, and if anyone's never seen an aerospike in,
have to write that down,
in action, then Google it and see if see a YouTube video of what an aerospike looks like. It's very strange, looks completely different to a rocket engine. They're really cute, and I think there's potential for CubeSats because you don't need kind of complex gimbals to move the thing around.
Okay,
and not many moving parts. So people have made very short, very small versions of, not CubeSat scale yet, but it may be possible. So I think that'd be a lot of fun. I think not maybe completely impractical, but maybe significantly over spec, but it'd be really fun to play.
So that's sort of one for the engineers to really sort of chew the fat on, or
absolutely,
cut their teeth on. Yeah. Wow, that would be fun, having those kind of problems and then having to try and find solutions and innovate. And
I think, and the great thing is, we can there's a company in New Zealand called Rocket Lab, which we can launch stuff with them for, I think it's 80k Australian. So it's not super cheap, but it's the kind of thing that we can be launching something every year, so trying out some of these technologies. So I think it's great to be here doing projects like this, because I can get, we can have students at Curtin working on projects where the stuff they build as an undergrad or as a PhD, they can test it out a couple of times in space. Yeah, which is...
Oh my God.
Yeah, I like that.
So what's the goal here with the application for the CubeSats? Does this tie into the satellite tracking that you mentioned, or is this a separate?
It's a separate thing. So I think that that there will be so the kind of long-term goal for me with that sort of 5-year goal is a mission, something on the scale of like a lunar orbiter or an asteroid flyby, that kind of thing. And then all the science that we can get out of that, and we can get a lot. But then in the run up to that, developing that, we can kind of follow a path that takes us through building components and systems and subsystems, all of which will have relevance for Australia's growing space industry. So we can kind of help develop that, and the IP that we've develop. We can work with Australian industry to do that. So, but that path that is a kind of a separate thing from the satellite tracking, which is a whole other project that we're working with industry on. Yeah.
Yeah. So this is so a couple of years ago I watched Gravity.
Awesome.
And outside of it being a movie that I love my space films, but this one I didn't particularly like so much. I think a lot of the camera angles gave me like vertigo sort of feelings.
Okay.
But and I hate to use like a Hollywood blockbuster to pose a question, a scientific sort of based question to you, and a Sandra Bullock blockbuster. But when they get struck by all the debris that's orbiting the Earth,
yes.
and that sort of sets off a chain of events, is really not a good time. It got me thinking about how much space junk is actually out there, and I've seen like sort of little animations of we're just littered with satellites and got whatever else sort of orbiting the Earth. And I did wonder, like, how do we keep a track of all of that, and how do we not have constant like impacts and things going on? Like, maybe that's my ignorance, but
no, it's not. It's I mean, the kind of freaky thing with that movie is that it's really in terms of all the sorts of movies like that, space movie, whatever, it's really grounded in fact. I mean, it might happen quite as fast as it's shown in the film.
Yeah, it
might be weeks rather than days, but not much longer than that. And on that sort of timescale, you could pretty much take out everything in low Earth orbit, and it'd be trillions of dollars that we'd lose. Communications, we'd lose GPS, we'd lose just tons of stuff that we take completely for granted.
Could we lose Netflix? Someone said you could lose Netflix.
I think we might lose Netflix. So this would be bad. So now, so it's a really big deal to track this stuff. It's a really big deal to track all the active and inactive satellites and try and work out, really where they are and keep track of them. And then, we can kind of move them around so there's no more kind of impacts between satellites, so you don't generate more debris. And gradually, hopefully what's there its orbits will decay and we'll lose some of it. But if we have more events that generate a lot, then you could have a situation like the sort of gravity type situation. Yeah.
So what's the general premise of what you're about to do, or you currently are doing with Lockheed Martin in terms of satellite tracking? Like, is it based loosely off the Desert Firewall Network technology? Or?
It is.
Okay.
So we I realized that look, we've built these systems that can sit out in the middle of nowhere. We know we can get really good precision on a trajectory by triangulation. It surprised me that people had not done that in satellite tracking. They point a telescope, really expensive telescope, at a satellite and got a trajectory in an orbit like that. But if you see it from a bunch of different angles, you can get a really good orbit for like 1/100th of the cost, but of a similar sort of precision by triangulation. And so that seemed like a smart way of doing it. So we kind of did some preliminary studies to see, can we get cameras and lenses that would give us enough sensitivity to see a lot of satellites, and we can. And then start the project with Lockheed to sort of develop this. And the goal is really that it'd be a global system. And the idea is really that rather than just using really, really expensive sensors to get very precise information, but rarely, so you got a narrow angle on a telescope, you see it, that object, and then you have to kind of, you need quite clever models to sort of predict where it's going to be in 20 days time or something like that. We'll just see them all the time. So if it's a global system, we don't have to bother with clever models. We don't have to bother with really expensive, sensors. We just see everything all the time.
Yeah.
And you end up, you've got a system that's something like, it'd be kind of like air traffic control for space. So that's the goal.
How widespread would that network have to be for you to have constant monitoring, and like what's the depth of that would require?
So we're building this global fireball system. That's going to be about a couple of hundred observatories doing the fireball work. They're different systems than the satellite tracking ones. Satellite tracking network could be smaller than that, might be 100, 150 systems, and you'd be picking objects up, maybe 4 or 5 times a day, which would be kind of awesome. Yeah. So that project's going really, really well, and we've kind of demonstrated capability that's sort of, nuts in that how gorgeous it is. I'm really, really chuffed kind of how well it's gone actually, and it's I really hope that we can build that full system and roll it out. I think that'd be great. Yeah.
That'd be incredible. Yeah. So sort of looking to wrap up, is there anything you wanted to discuss that sort of...
I don't know. I mean, an interesting thing, that I thought about actually with Lockheed, and I've talked about with them, is that is the first time actually for me that I've worked with very closely with industry. Yeah, and it's really interesting to kind of have that. I've been in research my entire career, and you get used to all the kind of ins and outs of how universities work and how funding agencies work, and it's really interesting to kind of see something as a completely different rule book, and I found it's been great because it's kind of we've getting that conversation and learning each other's language has been lovely, and so now we're kind of at a point where we both do understand each other's language, and it's much more. It's very collaborative. It's very open. That's turned out to be a lot of fun. Yeah, so that's great too.
So you've got the CubeSats you're working on. You're working with Lockheed Martin. Something to look forward to for our viewers and listeners would be the Acerous potentially bringing back some material in 2023, which is definitely one to watch out for. So the CubeSats you're expecting to launch maybe at the end of the year, and that would be in New Zealand with that company that you mentioned before.
Exactly. Yeah.
That's something that's a much closer timeline. Definitely,
so that's a big one to watch out for. Yeah.
Yeah. That'd be incredible. It's really interesting to see how the Australian Space Agency sort of tracks along over the next little while, and I don't know what the size of I think maybe their budget is sort of in the order of millions at the moment. It's maybe...
I think it's 15 million is the sort of discretionary, what they've got. But it's worth keeping in mind that the UK Space Agency began with no more than that. Yeah. And now it's big, and they're doing really exciting stuff. They've had an astronaut on the space station, and because basically the UK government realised very quickly what the sort of return was in making that investment. And I think I wouldn't be surprised if Australia realises the same thing pretty quick. Happily, the agency has started with a similar remit to the UK one, that yes, we're not going to formally exclude blue sky research scientists, missions, university like blue sky departments and groups, and that's great. So it wouldn't surprise me if we in 5 years we're doing some pretty awesome stuff.
Yeah, well, it's something to look forward to. In closing, thank you so much for taking the time to talk to me. It's been really good. It's probably I'll probably go out and say it's been one of my favorite episodes. And
Oh, great.
there's been some crackers. So hopefully people watching and listening have enjoyed it as much as I have. And
Thanks, Billy.
no, it's been brilliant. And for everyone that's listening or watching on YouTube, you can get us on Facebook at facebook.com/Layman's Podcast. We're also on Instagram at Layman's Podcast. So that's you can sort of follow us there and keep up to date with what we're doing. We've got a lot of exciting podcasts coming this year. So thank you very much. Thanks. Thanks so much.
Thanks, pal. Nice one, lad. Oh, yeah.